It was really good to see everybody yesterday during the Zoom class. Those of you that could make it, I received messages that some of you did not get the message until late that we were meeting, and that's okay. I understand. Really, yesterday was kind of informal. Tomorrow's meeting, hopefully, you guys will have more content-specific questions that you might want to address that we can talk about as a group. What we're going to talk about today is section 2.13. This is where we're finding the confidence interval for a population mean when we know the standard deviation of the population. What this means is, and we kind of touched on it in the last set of notes, but what this means simply is that if we don't know what the mean is of the entire population, we want to establish some way that we can be confident that we know the mean lies within a range of values. So we looked at 95.44% a couple of times yesterday. What we're going to look at today, more specifically, is a 95% confidence interval, which is more common for us to use. Occasionally, you'll see a 90% confidence interval, and we're going to talk about that. 99% sometimes pops up, but it's kind of rare. 95 is kind of the standard. But what we're saying, though, is if we take a bunch of samples out of the population and we use those sample means, can we come up with a very narrow range of values to kind of limit where our population mean might lie? So what we're looking at today essentially is just we're going to be able to say we are 95% confident or 90% confident that the true population mean lies between value A and value B. And so when we're computing that, we're going to go ahead and jump into the notes here. When we're computing that, one of the things that we want to know is the confidence level has to be first expressed as a decimal. So 95.44%, you can see that right here. We would express that as 0.9544. And that gives us our value for alpha. So when we want to find the confidence level, it's simply the form 1 minus alpha, where alpha is going to be some number between 0 and 1. And we take our confidence level and subtract it from 1. And in the case of alpha being 0.9544, we would get 0.0456, which is going to be roughly, we'll say 0.05 for the sake of computation. And when we have that z-score, or not that z-score, but that confidence value for alpha, then we want to compute the z-score, and we're going to compute z sub alpha. And remember, when we use that notation, that simply means the z-score that has the area alpha to its right under the standard normal curve. Now, the standard normal curve table, the z table, gives us the area to the left of a specified value. So if we were wanting to find the z-score that corresponds to 0.05, if we have z sub 0.05, what we want to do is first consider 1 minus 0.05 is 0.95. And then we can go into our table and we can find 0.95 in the z table, and that is going to be from the areas, so we have to work from the inside out. 0.95 is going to fall between these two values right here. So our z-score that corresponds to that particular area is 1.645. And that's all we're doing with the z table. So hopefully you haven't lost that. If you have, I believe it is on the website for you to pull up and look at as you need. So here we're going to look at a couple of formulas that helps us calculate the confidence interval. The confidence interval, like I said earlier, generically would be between some value A and B. Specifically, the way we find the confidence interval is x bar minus z sub alpha over 2 times sigma over square root of n to x bar plus z sub alpha over 2 times sigma over square root of n. Sigma is our population standard deviation. N is our sample size. And and X bar is the sample mean. Okay, so once we find those values, then we can compute the confidence interval and come up with this range that works for whatever our confidence interval or level needs to be. So here's a step-by-step process. First, we assume that there is a simple random sample. We assume a normal population or a large sample. That's something we talked about yesterday on one of the questions. And then 3, we also know what the population standard deviation is. We're going to have to use the z-table. We're going to use the 2 formulas that I just highlighted previously, where we have x bar plus or minus z sub alpha over 2 times sigma over square root of n. And then we're going to interpret that interval. We're going to go ahead and we're going to jump into an example here. I do want you guys to make sure you read over these 2 notes right here. The first one is when to use the one mean z-interval procedure. It's for small sample size. The procedure should only be used when the variable is definitely normally distributed. For samples between 15 and 30, we want to make sure we eliminate outliers. And for large samples of 30 or more, then it can be used without any restriction. We can always use the z-interval procedure that we're getting ready to see here in example 1. So in example 1, we have the Bureau of Labor Statistics collects information on the ages of people in the civilian labor force and publishes the results. 50 people have been randomly selected. Their ages are displayed in this table. We want to find a 95% confidence interval for the mean age, mu, of all people in the civilian labor force. Assume that the population standard deviation is 12.1 years. So the first thing we want to do is find our alpha. So alpha, this is step 1 from the procedure. Alpha is equal to 1 minus our confidence interval, which is 0.95. So alpha is 0.05. And then we will find z sub alpha over 2. So it's going to be z sub 0.05 divided by 2, which is z sub 0.025. When we divide 0.05 by 2, we get 0.025. Then we're going to go to the table, and we're going to find the z-score that corresponds to 0.025 or 1 minus 0.025, which is equal to 0.975. So we look for 0.975 in our z-table. Pull it up here. 0.975 is going to be right here exactly. So that is 1.96. Go back over here and we get that z sub alpha over 2 is equal to 1.96. So we need to make sure we remember that value. Step 2 is to establish the confidence interval. And the confidence interval is going to be, let's see, make sure I'm not jumping ahead of myself here. Find the confidence interval and then interpret. Okay. So step 2, we have to take x bar plus or minus z sub alpha over 2 times sigma over square root of n. So let's first do we first need to calculate what is x bar. Well, x bar is going to be the mean of our sample set. I've gone ahead and added these values up. These total to 2,096. There are 50 values in the sample set. When we divide 2,096 by 50, we get 41.4. So there's our mean. That's our x bar for this set. So we come back over here to our calculations for step 2. X bar is 41.4 minus z sub alpha over 2, we've calculated to be 1.96 times sigma, which is our population standard deviation, over the square root of our sample size, to 41.4 plus 1.96. All right, and then all we have to do is type these into our calculators and simplify them, and what we end up with is 38.0 to 44.8, and these are in years. So part 3, or step 3 of the process, just says to interpret the confidence interval. So what we're saying here is that we can be 95% confident that the population mean age lies between 38 and 44.8 years of age for the population of the civilian labor force. Excuse me. Then when we move on, we are going to kind of talk about margin of error a little bit more. That's something we've discussed previously. Remember, our margin of error is the point estimate plus or minus the margin of error. And here we have kind of a visual representation, but the way we calculate the margin of error is z sub alpha over 2 times sigma over the square root of n. And you can see, like I said, here's the visual representation of what that's showing. Here's our mean of the sample, and we add some number to the right of that, and that takes us to the upper bound of our confidence interval. We subtract the same number from our sample mean, and it takes us to the lower bound of our confidence interval. So in example 1, we applied the one mean z-interval procedure to a sample of 50 people. Part A just simply says to determine the margin of error for the 95% confidence interval. We want to first recall that here n is equal to 50. Our x bar is equal to 41.4. We've already calculated that. And our sigma is 12.1. And determine the margin of error for the 95% confidence interval. The error formula is E equals z sub alpha over 2 times sigma over square root of n. We substitute in the values that we know. We calculated or found z sub alpha over 2 for the 95% confidence interval to be 1.96 times sigma is 12.1 over the square root of 50, and we will get a margin of error of 3.4 years. So what that means is if we take our mean, which we computed a second ago to be 41.4, and we subtract 3.4 from that, that gives us our lower bound of 38. If we add 3.4 to that, we get 44.8, which is our upper bound of the confidence interval. Now, part B, it asks us to find the confidence interval at a 90% level based on the same data. So in this case, our alpha is equal to 1 minus 0.90, which equals 0.10. So z sub alpha over 2 is equal to z sub 0.05. When we divide 0.1 by 2, we get 0.05. And again, we would go back and we would find that 0.095 in our table. Pull this up here. Uh, 0.095. We already found that once. There it is. It's going to be approximately 1.64, 1.645 rather, and because it falls between these two values right here. So we get that this is equal to 1.645, and then all we have to do is substitute those values into the formula, and we have 41.4 plus or minus 1.645 times 12.1 over the square root of 50. And if we type those two equations into our calculator, we're going to get 38.6 to 44.2. And we want to compare those two margins of error, or two confidence intervals for part C. The 95% confidence interval has a larger spread than the 90% confidence interval. The 90% confidence interval is reduced to 38.6 to 44.2. So the difference between these two values is less than the difference between these two values for our 95% confidence level. And then we want to compare the margins of error. Well, we've already calculated the margin of error for the 95% level. It was 3.4 years. That's for the 95. The margin of error for the 90% confidence level is going to be computed in the same fashion. We take z sub alpha over 2, which was 1.645, times sigma over the square root of 50, and we end up with 2.8. So what we notice right here is that the greater our confidence level, the wider our margin of error is going to end up being. If we wanted to be 99% confident that our value lies within 2 points, then it would actually be, it'd probably be closer to 4 years or 5 years maybe for the margin of error. So the tighter our confidence interval, the greater our margin of error becomes. You can see that here with 95% it's 3.4, with 90% it's 2.8. So when we look at what I just mentioned, for a fixed sample size, decreasing the confidence level decreases the margin of error and improves the accuracy of a confidence interval estimate. So hopefully intuitively that makes sense to you. If we wanted to be 50% confident that our mean lies within 2 values, we're going to have a very, very, very narrow range or margin of error in the case of whatever the problem might be. So when we start talking about sample size and accuracy, that leads us to leads us to example 3. Part A, we're still using the same numbers from example 1. So part A says determine the margin of error for the 95% confidence interval. We have already calculated that in the previous example, which was 3.4 years. Part B says a random sample of 200 people gave a mean age of 42.2 years. Find the confidence interval for mu based on that data. So for part B, we have n is equal to 200. We have our x bar is 42.2. And then we already know that 95% always will correspond to a z-score of 1.96. So we don't have to keep going back to the table and looking that up. So when we put this into our formula, we have 42.2 minus 1.96 times sigma, which is still going to be 12.1 over the square root of 200, because that's our new sample size. And then that range will go to 42.2 plus 1.96 times sigma over the square root of 200 in this case. So when we evaluate those with our calculator, we get 40.5 years to 43.9 years. Compare the two 95% confidence intervals. With our previous confidence interval of a sample size of 50, we had, let me go back to where I wrote that down. It was 38 to 44.8. So this is 95%, a sample size of 200. 95% with a sample size of 50 was 38 to 44.8. So we've increased the size of our sample and we've narrowed the range of our confidence interval, but we're still using a 95% confidence level. So now we're even more precise with the confidence interval, because we've increased the sample size. Part D just simply wants us to calculate the two margins of error. We've already calculated the margin of error for 50 people. The margin of error for 200 would be our z sub alpha over 2 times sigma over the square root of 200. And when we simplify that, we get 1.7. So the margin of error when we increase our sample size to 200 becomes 1.7 years, as opposed to the 3.4 years when our sample size was only 50. And then that note here in the middle of the screen clarifies what we've just said. For a fixed confidence level, increasing the sample size decreases the margin of error and improves the accuracy of the estimation. Then we have some cases, maybe we want to find out what sample size do we need to guarantee a certain confidence interval level, maybe 95% or whatever it might be. So, and that's what we see right here in red on this formula. The sample size required for a 1 minus alpha level confidence interval for mu with a specified margin of error is given by the formula n equals z sub alpha over 2 times sigma over the margin of error quantity squared. So here we have to know what z sub alpha over 2 is. That's our confidence level. We have to know the population standard deviation, that's sigma. And then we have to know what our desired margin of error is going to be. So if we wanted to narrow this margin of error down to say 1.5 years, that would be our value for E. We would substitute that in, and then we would be able to come up with what size sample do we need to take to guarantee 95% confidence level that our population mean lies within a margin of error of 1.5 years to either side of the true or of the sample mean. So again, we're using the same data here in example 4. It says determine the sample size needed in order to be 95% confident that mu is within 0.5 years of the point estimate x bar. We need to recall first that sigma is still 12.1 years. We are not changing the standard deviation at all. So when we take the formula that we just looked at, it's n equals z sub alpha over 2 times sigma over our margin of error quantity squared. In this case, we don't know what n is, but we do know that z sub alpha over 2, which corresponds to 95%, is 1.96 times sigma, and our margin of error is 0.5. And then we square that. When we type this in our calculator, we get 2249.79. What you want to make sure you always do, though, with these numbers when you're calculating the sample size is to round up every single time. If that was 2249.03, we would still round it up to 2,250. So what this tells us is that if we take a sample size of 2,250 people, we can be 95% confident that our mean is going to be within 1.5 year of the sample mean. So that's we've increased our sample size and we've narrowed our interval for the confidence level. Part B, find the 95% confidence interval for mu if a sample of the size determined in Part A has a mean age of 43.8 years. So here again, we're going to go with this is Part B. Z sub alpha over 2 is 0.025, which we've already figured to be 1.96 several times over. Sigma is still 12.1, and our x bar is going to be 43.8. And n is what we calculated for Part A is 2,250. So we get 43.8 plus or minus 1.96 times 12.1 over the square root of 2,250. And when we type this in our calculator, we get 43.3 to 44.3. That's our confidence interval for 95%, given a sample size of 2,250 people, that our mean will be within 1/2 year of the population mean. Take just a couple of seconds after we're done and read through these 2 bullet points, and then you guys are ready to knock out the homework. This is more computation than anything, and it should be fairly straightforward. But again, though, you guys know, if you have questions, please just ask me, and I will be happy to answer them. Again, I hope you guys are having a great day, and I'll be talking to you tomorrow in our Zoom class.